Okay, we're recording. All right, so last time we were talking about the chain rule, and there are different ways you can think about the chain rule, but let me just remind you, when you have a composition of functions like we have here, and if you want to look at that composition that views these variables as functions of those variables, right? And I wrote it vertically here just for kind of space reasons. Also, it doesn't matter, and it's good to be accustomed to different notations and different conventions. But in that case, so you can write down sort of a coordinate version of the chain rule, but you can also write down this matrix version of the chain rule. And the big idea is that if you organize the partials of a given function, there are, after all, n different variables that you could take partials of with respect to each of m different input variables, right? That gives you an array of different partial derivatives. If you organize them like this, where the input variables correspond to columns, right, and the output variables correspond to rows, right? So organized, the chain rule corresponds to matrix multiplication. It's kind of a phenomenal fact. So again, this Jacobian matrix, these are called Jacobian matrices, times this Jacobian matrix gives you the Jacobian matrix of the product, namely all of the partials of the eventual outputs with respect to the original inputs. So, fantastic little bookkeeping tool, right? This organizes so much. This is, a whole bunch of different instances of the chain rule all in one equation, right? So, the chain rule as applies to that partial derivative is, this dot product. And the chain rule as applies to, let's say this element, this partial derivative is this dot product, etc. So again, a bunch of different statements all encapsulated together. So that's really nice. Now, there is something, there's a special case of that I want to talk about. Let's think about what happens when in your composition of functions, there is exactly one original input variable. So in other words, the what I'm going to now call the x variables, and then which then lead to the y variables. They're all functions of t, right? Just the one input variable. And I choose t because again, I do kind of want to encourage you thinking of the metaphor of t standing for time. I think it's very helpful, very convenient. Okay, so if x and y are all eventually functions of time, well, let's write down the product version, the matrix version of the chain rule. Now there's only one input variable, so there's only one column. Okay. But now furthermore, let's look at the eventual composition. The composition function takes y, all of the y variables, all of the y coordinates as being functions of t. Position, again, as a function of time. So, likewise, then, with only one input variable, there's only one column. And if you look carefully at these columns that are two of the three matrices involved here, notice they're exactly the velocity vector. Right? So we talked previously about when you have a parametric curve, and by the way, each of these functions, the green function and the purple function, both give position in some output space as functions of time. Right? So these are literally parametric curves, and these are literally their velocity vectors. Here, in fact, let me, so velocity vector and velocity vector. So this gives us what I'm going to call a really powerful interpretation of what this matrix is. This matrix, again, our notation for this is the Jacobian J, capital J, representing all the partial derivatives of that function. That Jacobian matrix, what it does is it multiplies by input velocity and it gives you, as a result, output velocity, which I'm going to draw in a picture here. Oh, and you know what? Just to make sure I get all the colors straight, let me do it like this. So, yeah. So there's an input velocity, a velocity in my domain. The function g that I'm looking at takes points in the domain and produces points in the target, and that input velocity corresponds to this output velocity. Is everybody on board? There's a really nice interpretation of the Jacobian matrix. So, it's kind of hard to see that coming. When you first start writing down versions of the chain rule, here was our first version of the chain rule. It kind of looks like it's a statement about coordinates, and that's fine and all. But then, I suppose as a bookkeeping tool, we can think of it as a statement about matrices. All right. Bookkeeping organizationally, thumbs up. We like that. Here's where it becomes geometrically actually pretty meaningful. This matrix, relates input velocities and output velocities. Don't forget what a velocity is. A velocity is a rate of change, right? And so another way to say it is this matrix, the Jacobian matrix, relates input changes to output changes. Again, that's our primary interpretation of what a derivative is. So in the same way that we made the case that the gradient vector could, if you look at it the right way in certain circumstances, could be viewed as the derivative. It behaves just like the derivative does. Well, now also, slightly different point of view, the Jacobian matrix behaves like a derivative, right? It relates input velocities to output velocity. It does what derivatives are supposed to do. So, FYI, arguably even more fundamentally than the gradient vector, the Jacobian matrix is the derivative. And depending on the context, when you're talking about multivariable functions to, whoever is, depending on the context, I guess is the key word there. And people talk about the derivative of a multivariable function. Very often what they mean when they said derivative is this. They mean the Jacobian matrix because of this role that it fills. Okay. All right. Right. Okay. So I'm going to move on now to second derivatives, and this treatment that I have in the Math212 notes is fine, but I believe it's a little bit better written here in my Math219 notes. So I'm going to switch over page 37 of the chapter 2 Math219 notes, and here we go. We're going to ask what happens if I need to take a second derivative of a composition. Well, composition means this is going to involve the chain rule, but second derivative, we have not previously entertained. So the big idea, mostly I'm going to show you how this works by example. We're just going to dive right into an example, but the big idea to be on the lookout for is if you have one variable that's a function of others, then its partials are also functions of those same input variables. That's ultimately the big point. So let's dive in and see how this works. Here is the example that I want to entertain, and that is this right here. You'll notice I've added, over here in purple, I've added some extra little details. In Math219, we would have already covered polar coordinates and spherical coordinates and stuff like that. And the way Math212 is arranged, we haven't. It's no big deal. All you're going to need to know about polar coordinates in this example is that, well, for one thing, that polar coordinates is a way of keeping track of where you are. Just like rectangular coordinates are a way of keeping track of where you are in the XY plane, polar coordinates is a different way of keeping track of where you are in the XY plane. You keep track not by an x-axis and a y-axis, but you keep track by an angle indicating what direction from the origin, and then a number called r, which tells you, loosely speaking, how far to go in that direction. It's just a different way of keeping track of where you are. The other thing you need to know about polar coordinates is these formulas right here. We will draw some pictures, do some trig a little bit later, and justify this, but for the moment, I claim these are the formulas. Trust me, if you would. Okay. So, with that said, and with z being a function of x and y being functions of r and theta, how would I compute the second partial of z with respect to r? There's our question. Now, let's draw a little roadmap here of what we're talking about. Z is a function of x and y, so indicated on our diagram. Right? X and y, as previously discussed, are functions of r and theta. There we go there. Right? Now, do notice that the purple function I have an explicit formula for. The blue function I don't. I just have a name for it. It's called f. That's it. Right? And so we can't really actually compose these functions explicitly because we don't know all of these functions. All right. Is everybody with me? So that said, to the posed question of, what is the partial derivative of z? Well, the first partial derivative I need to take anyway, partial of z with respect to r. I have two paths. There's the x path, that gives me an x term. I have I'm running out of colors, dark green, a y path, that gives me a y term. And some of this I can simplify, no big deal. After all, I know exactly what x is. X is r cosine theta, and I can straight up compute that partial derivative. Likewise, I know what y is in terms of r and theta. I can straight up compute that partial derivative. Everybody okay? All right. Now, that said, what can I do with, try not to erase the wrong things. What can I do with this thing? Can I compute the partial of z with respect to x? No, I don't know what that function is. So I just have to leave that as partial of z with respect to x. So what we're effectively doing here is computing a general formula. And so we're just going to leave it as partial of z with respect to x. But I am going to change the notation. I'm going to write it with this subscript notation. It's just going to kind of look better on the page. Okay. All right. So now this was not the original question. The original question was to compute the second partial of z with respect to r. I've only computed the first partial. So I'm going to need to take an r partial of this thing. I'm going to need to take an r partial then of this thing. How am I going to take an r partial of that thing? Well, what we're going to do is we're going to append our diagram. Now, here's what we previously had. Oh, that's old news, right? But I'm going to be taking an r partial now of this thing, which involves this thing called zx, and zx isn't on my picture up here. Well, what am I supposed to do? Right? How would I take an r partial of zx? And let me show you a nonsensical thing that some students will write down. Some students will say, well, let me not do that. If I were to want to take an r partial of zx, some students think, how about zxr? I claim that is nonsense. Let me explain why that's nonsense. Because writing zxr suggests that z is a function of a collection of variables that includes both x and r. Right? So this presumes that z is a function of 4 independent variables. And they're not. They just aren't independent. X is explicitly a function of r and theta. For example, you cannot talk about the partial with respect to r of this function, because if you were going to take the partial with respect to r, you'd have to have r be a variable and then have all the other variables be constant. Be constant. And again, this is nonsense. You can't. There is no way to let r change and have x, y, and theta all stay constant. If you change r, you're going to change x and y. Right? So this is just, it doesn't, the whole thing is crash and burn nonsense. Is everybody on board? Does everybody see the problem here? Right? So you really can't just do this. This is total garbage. What you've got to do is recognize that this thing, zx, that we want to take a derivative of with respect to r eventually, you've got to recognize that it is an expression. It's a variable in this diagram. It's a function of other things. What is it a function of? And then we can talk about how the diagram will instruct us to actually take partials of it. So zx, as previously noted, being as it is a partial of z, just like z, then it is a function of x and y. And being as it is a function of x and y, I will indicate thusly on the diagram, my new appended diagram. Is everybody on board? Cool. All right. So it's all over but shouting, frankly. We got to be careful. And I will advise, by the way, when you're working a question like one of these, don't go too fast. Take your time. Don't try to leap over 3 algebraic steps all in one bound, right? You're going to get yourself in trouble. It's easy to make mistakes. But anyway, here we go. The original question was to compute the second partial. Namely, we now need to compute the r partial of the r partial that we just computed. Right? So how am I going to take the r partial of this r partial? Well, we're going to take it, again, one little step at a time. But before I get into the chain rule and trying to keep track of stuff, let's draw a picture on here. When we say partial with respect to r, that means that r is a variable, but partial means that theta is to be understood to be a constant. And before I do anything, let's capitalize on that. We're taking a partial. Theta is constant as a result. That means that cosine theta is a constant, and I can factor it right out. Likewise, sine theta is a constant. I can factor it right out. And then rewrite very nicely that this thing that I want to compute, I can think of instead as this expression right here, that, again, simplified nicely. Now, we got lucky there, and it just happened to be that one of the factors in our product rule just happened to be a constant. Life is good. Sometimes. It won't always be, right? Sometimes we'll have to write down the product rule first, and, that gives us more terms, but anyway. Okay. So now, how am I going to deal now with this thing? Partial of zx with respect to r. Well, as planned. To answer this question, I need it on the diagram, and as planned, zx is now on my diagram. There it is. There's zx. Taking its partial with respect to r being also on our diagram right there. How do I compute partial derivatives? What does the chain rule tell me to do? The chain rule tells me to look at the paths between these two variables, and, well, there's what you might call an x path, which gives me an x term, and there is what you might call a y path, which gives me what you might call a y term. And so this partial derivative of zx with respect to r, chain rule, as per this diagram, tells me it's this expression right here. How are we doing? Everybody see what happened? Okay. Right. Then, of course, constant cosine theta Nothing happened there. That just comes along for the ride. You can make an analogous argument, and this is a healthy exercise I'm going to encourage y'all to do for yourselves. But think through how you would let me just get rid of all of that. How would you compute the partial of zx the partial of zy with respect to r, right? Because that's what that is. How would I compute that partial derivative? Well, again, you think about the various paths. Paths correspond to intermediate variables, which correspond to terms in the chain rule. I claim it gives you this. And then again, this constant comes along for the ride. So think through those details, healthy exercise. Is everybody with me? Okay. All right. And now it's kind of all over but the shouting, frankly. Again, we already know what y is as a function of r and theta. I can compute this r partial explicitly. And likewise, that I can compute explicitly. And likewise here and likewise here. So that's just a rewrite, basically. Then there's the question of what am I going to do with this thing, the partial of zx with respect to x. Oh my gosh, I'm scared. Is this a diagram problem? Do we need to use the chain rule here? Slow down. Let's let the diagram be our guide. I'm taking the partial of zx with respect to, let's see here, well, x. This isn't part of a composition. There's no chain rule to be worried about. No intermediate variables. It's just the partial of zx with respect to x is just, well, it's zxx. Exactly as you would kind of expect and hope. Is that cool? All right, and then likewise, that, and that, and that. So, couple of little rewrites. Again, thank you, diagram. Such a big fan of the diagram. Please don't try to do these chain rule problems without writing a clear, complete diagram showing all the players involved and all the connections like I've done here. It's essential. It's so convenient and powerful. Okay. And then you move some things around and collect some terms, and this is your final answer. And again, there are some, unspecified things in here. There's this, zxx. How do I simplify that? Well, I can't. This is just a second partial of a function I don't know. So that remains as it is, right? And likewise for that and for that. Okay. Questions? Yeah.
I noticed you wrote the dy over dx as dxy, and I remember last time you said something about
yeah, no, that's great. That's right. Yeah, good call. So, good catch. Let's talk about this partial of zy with respect to x. I probably should have written that as zyx. Absolutely. I'm writing it instead as zxy, and that's because I'm assuming here, and I hope I wrote it down. Oh, did I write it down? I didn't write it down. Okay, shame on me. I need to fix these notes. What I should have written here is that this function is C2. And so we're going to assume that I meant to write that down. I meant to assume that this function is C2, and when you have a C2 function, you can switch the orders of the partials, and it doesn't matter.
Could you remind me what a C2 function is?
C2, it's a function where the function and its partials and its second partials, so partials all the way up to order 2, are all continuous. Yeah. Right. So that is an assumption that we need to make this work, and I didn't write it down. Shame on me. Right. Okay. Is everybody good? Good catch. Thank you for that. All right. Okay. Now I want to show you all a quick application of this. I think this is a really good one. I'm gonna have to make some references to stuff that we haven't really spent much time with. The very first reference that I'm going to have to ask you to take on faith is that this thing called the Laplacian operator is extremely important. It is, I wrote down some equations previously as to how it works, but the way waves flow, the way heat moves, how electrons behave in the presence of protons in a electric field, etc. This is just really important in those discussions, and of course these are huge questions in engineering and physics and chemistry, etc. Okay, so all that said, now the next thing I'm going to have to ask you to take on faith is that there is this stuff called spherical coordinates, and spherical coordinates, kind of like polar coordinates, is a way of keeping track of where you are in space, and there's some formulas to write down and stuff, but the main thing that you need to know, aside from the fact that it's a coordinate system, it's how we keep track of where we are, but now in 3 dimensions, details to follow. There are some standard relationships that tell me how to compute x, y, and z as functions of these spherical coordinates, rho, phi, and theta. Greek letters, rho, phi, and theta. Okay, so the rest of the details will come later, and you don't need to know those here. So this Laplacian operator, so important in so many different ways, written in rectangular coordinates like this, I claim can be written, now this is the same thing, mind you, this is still the Laplacian, but it can be written in spherical coordinates like this. And how, I pose, could I possibly relate these things to each other? Right? These look like completely different expressions, and frankly, this second one down here looks pretty nightmarish. Right? At a glance, yikes. Why would anyone ever choose this one over that one? I mean, right? I mean, who would... That just seems like make work, and we don't want to do that. Okay, first, how do I know that these things relate to each other? Well, I can compute, for example, a second partial of f with respect to theta by using this diagram, thinking about paths, computing a first partial, and then, as I did on the previous page, just keep going and compute a second partial. And there's a lot of details involved, but you can absolutely just compute this thing here. You can just straight up compute that expression. And likewise, you can straight up compute that, and you can multiply by sine phi, and then you can take a phi partial of that, and you can then multiply by this fraction. You can just straight up compute all these things, and when you do, and there's a lot of details here, and I am not encouraging y'all to do this. This is, wow, a lot of work. More than I think is worth it. And, fingers crossed, hopefully your future physics and engineering professors won't make you do this calculation on your own. If they do, I'm sorry. But lots of effort goes into this. But the punchline is that all of these expressions, when you add them all up, a lot of cancellation happens and they add up to exactly this. Okay, so this idea of second derivatives with the chain rule allows you to rewrite the Laplacian. Now, who cares? Well, here's Laplace's equation. And here then is, here is Laplace's equation applied to this function right here. Color changes. This function f, written in rectangular coordinates, Laplacian in rectangular coordinates. And now here again is the same Laplace's equation now applied to the same function f, just now written in spherical coordinates. And again, the Laplacian, previously written in rectangular coordinates, now written in spherical coordinates per the results of the horrifying computation that I waved my hands at above. So what we have here are two different alternatives of doing the same thing. By the way, y'all may recall one of your homework exercises is to do this one. And you may have already done that. If you haven't, no problem. You'll do it. I forget when it's due. But anyway, it's this is a computation that you either have done or will do. And it's pretty annoying. It's not that bad. It'll take you, 15 focused minutes or so, right? But But anyway, nevertheless, I'm going to call that hard to compute. And now let's look at the alternative. The alternative over here instead looks worse. I claim it's not worse. I claim it's way better. In fact, I'm going to do this second calculation here right now in front of you. And I'm not even going to have to write anything down. It's that easy. This is falling down simple as follows. Let's look at partial derivatives with respect to theta of an expression that doesn't have any thetas in it. 0. Instant 0. We're taking a derivative of something with respect to a variable that isn't there. We're a third of the way done already. Likewise, now let's look at this term here specifically. The first thing it does is it says let's take the phi partial of this. Again, no fees. That partial derivative, 0, right off the bat, right? And so this term, all zeros also. And again, in a snap, right? It's looking good. Things are looking nice. Lastly, let's take the rho partial of this function that does have a rho in it. And so here I don't get to just wave my hands and declare 0. But it's an easy partial. I'm taking a partial with respect to rho of constant over rho. That's going to give me a different constant over rho squared, which I then multiply by rho squared, which gives me just a constant. And when I take a partial of a constant, I get 0. And so again, this whole thing here turns into 0. And so we're done. And this is 0 as required. Again, way, way easier than rectangular coordinates. Does everybody see what happened there? I mean, again, I ask you to take a bunch on faith in terms of the how the spherical Laplacian works out. But big win. So what you're going to find when you, at some point in the future, are doing any kind of physics or engineering in 3 dimensions, where there is an intrinsically spherical aspect to the problem, such as, you look at this function right. Let me get rid of the mess. You look at this function right here, right? This electric potential function. Electric potential depends on distance from the origin. There's an physically intrinsic spherical aspect to that. Distance to the origin is the major player. In those cases, your life is going to be way better if you do it in spherical coordinates. As a rule, there may be some exceptions out there, but usually rectangular coordinates attacking something that's intrinsically spherical is just worse, and spherical coordinates with spherical functions, spherically nice functions, just tends to be better. Okay, so powerful idea, huge win, and ultimately comes from the chain rule, and in particular the second derivative chain rule method that we outlined in this example. Okay, moving along. Let's see here. Yeah, okay, so the next thing we're going to talk about the implicit function theorem. So this is one where I really do have to kind of rein myself in. It's possible to spend an hour and a half talking about the implicit function theorem, and we just don't have time for that. So basically what I want to do is entertain this circumstance here where you have an equation where x and y are just variables in an equation, which of course you can always view as, just move all the terms to the left side. You can view any equation as stuff equals 0 or stuff equals constant. Doesn't matter. Either way is fine. But let's suppose I want to view y as being a function of x. Now, real quick, why would I want to view y as being a function of x? What's the point of this? Who cares if y is a function of x? The reason that I would want to do this is that, for example, at a point like this one, I might want to talk about that slope which I am tempted to write as dy dx. Oh, wait, I can't talk about the derivative of y until I know that y is actually a function, at least nearby. I mean, if there's some, the curve goes up, straight up above it somewhere really far away, we kind of don't care about that. We can ignore that. But at least locally, I need to know that the curve represents something that passes the vertical line test, and I can therefore view as a function, because you can only take derivatives of functions. This is a big point here, actually. A lot of students misunderstand. You can really only take the derivatives of functions. You cannot take the derivative of a bicycle. That's not a thing, right? Functions. So now it's tempting to say, well, yeah, fine, okay, but whatever. Do the algebra, just solve for y. Maybe you can't solve for y. And then you have to ask yourself the nasty question. Maybe the reason you can't solve for y is because, well, the algebra is ugly. But maybe the reason you can't solve for y is because locally, such as in this case right here, looking at that point, the part of the curve at that point, it doesn't matter how little you're looking at, it's going to fail the vertical line test. At this point right here, y is not, in any sense, a function of x. And I remind you, if it's not a function, you can't talk about its derivative. It's not that you can't compute its derivative. It's that there is no such thing as the derivative of y at that point in this case, any more than you can talk about the derivative of a bicycle. It's not a thing. It's a little scary thought. And what happens in a lot of contexts, especially high school calculus classes, is they kind of sweep this point under the rug, and they start, you take this expression and start applying symbolic manipulation of calculus to it and whipping things around and taking derivatives of whatever you feel like because, well, it's a variable. I guess it's a function. I can do whatever I want with it. At treating it as if it's a function when you have not established this yet. Right? This is not okay. It's a really big problem. Okay. So how do we establish that the something that I want to treat as a function actually is? Here's the basic idea. And again, I don't want to get too into the weeds and rigor about this. So I'm going to propose that, roughly speaking, the problem is, as in that example, if the curve is wrapping under itself, that's ultimately the problem. That's why that's why the vertical line test fails, is because the curve was wrapping under itself. And if the curve is wrapping under itself, if the curve is wrapping under itself like so, then that means that the tangent line to that curve is vertical. And that means, now keep in mind, this curve that we're interested in, this curve has an equation that we've written down. That curve has the equation force a habit. F equals 0. As I move from this point, as I move along the curve, well, I mean, I hope this is a pretty believable statement. If you're moving along a curve on which f is not changing, then f is not changing. That's kind of almost a tautology, right? But if you're moving in such a way that you're staying on the curve defined by f equaling a constant, then f remains constant and is not changing. But now let me say that slightly differently. If you're moving, given what we have here, along the curve means vertical. That means in the y direction. Now, as you move in the y direction, f is not changing. And another way to say that is, as you're moving in the y direction, namely partial derivative with respect to y, the function's not changing means that derivative is 0. Is everybody with me? Okay. So now, what does this tell us? Why are we writing all this stuff down? And the big idea is that if we have a problem, then the partial with respect to y will be 0. And now I'm going to do what's called the contrapositive. I'm going to take that statement and I'm going to say it backwards. P implies Q is equivalent to not Q implies not P. That's called the contrapositive. It's a convenient little logical construction. But so in this case, the contrapositive is if the y partial is not 0, then that definitely doesn't happen, because if it did, the y partial would have been 0, and we're assuming it's not. So if the y partial is not 0, then there's no problem. None of this is happening, and therefore y is at least nearby locally. I can think of as a function. Yeah.
So just to clarify, the implicit function theorem tells us whether or not a function, like a curve, is a function or not.
It tells us whether or not that's one way. That's a reasonable way to think about it. Yeah, but specifically, the implicit function addresses when I am looking at an equation that I have written here, importantly, as a level set of a function. Right? It helps me know when one of the variables in that equation can be viewed as a function of the other. Yeah. Right. Exactly. So that's the 2-dimensional version. Here's the 3-dimensional version. It's shockingly similar. And that is, let's suppose I have now an equation of 3 variables. Namely, suppose I have a surface. Like so. Can I view z as being a function of x and y? Now you can see how this is kind of a 3-dimensional version of what we just talked about. Well, sometimes yes. I mean, if I were looking at a point up here, for example, then yeah. I mean, just let's look at this piece of the surface, and locally passes the vertical line test, and at least nearby, I can think of z as being a function of x and y, and there's no problem. It's all good. Go ahead, and at that point, feel free to treat z as being a function of x and y. Right? And it works fine at that point, and it works fine at, frankly, most of the points on this surface. But something bad happens at that point. If at that point I try to say, oh, well, let's just look nearby, and nearby, that's a graph. Nearby passes the vertical line test. No, it doesn't. Right? So nearby that point, the surface has wrapped under itself, and therefore it will fail the vertical line test. No matter how small of a little yellow region, no matter how nearby that point you restrict your attention, it is at that instant in the process of wrapping under itself, and therefore it will have wrapped under itself, and therefore you will not be able to treat z as a function. So again, how do we identify this? Well, if you have a problem, that problem looks like this, that the surface is wrapping under itself, which means that you have a vertical tangent plane. And if you have a vertical tangent plane, that means that as you move in the z direction, you are moving along the surface on which f is not changing by design, and that means that the z partial would be 0. So again, the contrapositive of this statement, you say all problems would require the z partial to be 0. The contrapositive is that if the z partial is not 0, then you don't have a problem. Though totally analogous to our previous result, if you want to view y as being a function, if you want to view y as being a function, then you need the y partial to be non-zero. Here, if we wanted z to be a function, we needed we needed the z partial to be non-zero. And this generalizes. And you can think through various different versions of this if you like. You don't have to. But this generalizes even to n variables. Again, please don't try to draw a picture. You can't. Right? But I'm going to appeal to your intuition, your willingness to believe that patterns continue sometimes, this being one of those times. If you have an equation thought of as a level set of a function, and if you want to view one of these variables as being a function of the others, whatever variable that is that you want to view as a function, that's the partial that needs to be non-zero. And if it is, you're good. No problem. Go ahead. And notice how easy it is to check this. All you have to do is make sure that you identify clearly what is the function. Specifically, you need it to be a function on which the surface is described as a level set. What is the variable that you want to view as being a function of the others? And then just compute that partial, make sure it's not zero, and declare victory. That's kind of all there is to it. Is everybody on board? Okay. All right. So now, okay, I'm going to show you an example in a couple of minutes. But I do want to, before we get to that, I want to talk through the more practical matter of, okay, fine, but how then would I take derivatives of, let's say, xi? If it's a function of these other variables, if it is a function, then I should be able to take derivatives of it. And how would I do that? How would I take the partial derivative of xi with respect to xj? Let's say. Right. Okay, now there's different points of view that you can take on it. Back to my 219 notes, page 47 of the chapter 2 notes. How would you take the derivative? The sort of full and complete point of view involves making this diagram in which we're going to apply the chain rule. And frankly, though, it gets a little hairy looking, and I'm going to, rather than look at this full version, I have a streamlined version of this that cuts out all the stuff that ultimately isn't going to matter. And the reason I show you the complete version is I want you to see that there is a version of this diagram that satisfies the rules that I implored y'all to never break. Where here is a function, and here is another function, and the outputs from the one are the inputs from the other, and this is therefore a composition, and therefore we can apply the chain rule, and we kind of need that, right? But so I'm going to say, in this circumstance, for the purposes of avoiding ugliness, I'm going to commit what I'm going to call a victimless crime here. This what I've done here is hair raising. Right? You're not supposed to do that. This is a random diagram. This is not a composition of functions as I've described it strictly previously. But I claim that if we treat this diagram the way it kind of feels like it ought to be, it's fine. And I do think it's quite a bit easier to follow this argument than the one above. So this is what I'm going to do. Okay. All right. So here we go. Keep in mind, we started off with f being a function of all these other variables. We've got a method now for establishing under what circumstances I can view one of them as being a function of the others, not including itself, of course. And the question that I've asked is, how would I take the partial derivative of that now newly established function of the other variables with respect to, a specifically chosen one of those other variables? How would I compute this partial derivative? That's the question that we find ourselves looking at. Is that cool? The way I'm going to answer this question, and let me redraw here. I'm going to redraw this as I want to compute this partial derivative there. I'm going to answer that question by asking a different question that I already know the answer to. This is, again, a standard move in math. If you want to answer one question, ask a different question, and hope that the thing you're interested in shows up as part of that easier question, and then you can solve for it. We've seen several examples of this so far in Math 212. It's a wonderful little trick, very clever. Wish I'd thought of it. I'm going to ask first, what is the partial derivative of f with respect to that same xj? And I'm going to propose that there's an easy answer to this question. How does f change as I play games with xi and xj and stuff like that all along my original surface? Well, along my original surface, f is not allowed to change. F is constant. So altogether, this partial derivative has to be 0. Altogether, when you add up all the different ways that, all the different contributions to how f is changing, it's got to add up to 0. It's a constant. So, all right, so that's one calculation of this partial derivative. Now I'm going to compute it a different way. And again, the way we use the chain rule, and, again, in full recognition that I really should be on this diagram here, but I don't want to because it makes it ugly and weird, and it's just a lot easier to look at this diagram, and this is fine. There are two paths that I can take to get from xj to f. There's what you might call this path, which gives me this term with these two factors. And then there's this path, where there's really only the one factor because there's only the one arrow. Now that's just, thinking about the chain rule from the point of view of paths. Here there's two paths, so two terms. And then I recognize, well, wait a minute, the thing that I'm actually interested in is that partial, which I now see right there. Is everybody with me? Well, that's what I wanted in the first place, and so I can take this equation that came about from looking at something that ultimately I don't actually care about, right? And I can just now solve for what I actually am interested in. And, you move things around, divide appropriately, etc., and there you go. There's your formula. Is everybody happy? Now, you may recall, there's some weird things about the chain rule, and you cannot, it's tempting, very tempting to say, well, shouldn't I be able to just kind of take these things here and cancel them, and then the denominator of my denominator is my numerator, and shouldn't this then go up there? And then what's up with this minus sign, right? Kind of feels like I get the partial of xi with respect to xj without that minus sign. Well, this is all nonsense. You cannot cancel these things. Color mess up here. You cannot cancel these things. These represent changes in f, sure, but they represent changes in f in entirely different scenarios. In one scenario, xj is a variable and xi has to be constant. In the other scenario, xi is a variable and xj has to be constant. They're totally different partial f's. They represent how much f changes in different stories, basically. So you can't, if you're reading Lord of the Rings, and in that story there's a character named Steve, I know there's not, but if there were, right, a character named Steve in Lord of the Rings, and he does a certain thing, you then can't pick up a totally different book, and say, Steve did such, and so therefore this entirely unrelated fictitious character also coincidentally named Steve, right? And draw conclusions about it. No, they're totally different Steves. And these are totally different changes in f. Does that make sense to everybody? So please, please, please do not make this mistake of canceling those and then forgetting that minus sign. This minus sign is essential. And it's tremendously important on exams, and I want to explain why it's really important on exams. We've all made what's traditionally known as a sign error. It happens to everybody. It's okay. We all know, right? I'm perfectly willing to believe that y'all are competent with high school algebra, and yet it remains. And I've done it right here in class in front of you, right? Where there were 3 minus signs, and somehow I made that a plus, right? I mean, it's an easy mistake to make. That's not what this sign is. This minus sign is representative of understanding an entire argument about implicit differentiation and how to use the chain rule to understand implicit differentiation, and forgetting it. If you skip, if you oops and don't write this down, and if you write down just this alone, that honestly, I mean, at a glance, that just makes it look like, that you think that you can just cancel those partial f's, which of course you totally can't. It makes it look like you've completely missed the entire story of how this equation came about. It really makes it look like the writer, whoever would write such a thing, not only doesn't understand the valid argument, but doesn't even realize that they don't understand the valid argument, right? So it's a really bad look. And when the grader is going through and grading these things, the grader has to speculate based on what you've written how much you understand. So strategically, it's very important not to inadvertently cast yourself in a really bad light, right? And this minus sign right here is such a huge example of this minus sign, tremendously important. So I urge you, please be very, very careful when you're doing these problems. Make sure you don't forget that minus sign. Does that make sense? I hope that's satisfying. Okay. Here's the good news. All you got to do is remember it. It's no big deal. It's just a minus sign. Easy to remember. You get free points in some sense just for remembering that minus sign. So think of this as a glass half full, not a glass half empty kind of a deal. Okay, enough of that. All right, so let me show you an example. Now let's see here. Am I going back? No, I'm going to go back to here, to these notes. Yeah, here we go. So here is an example exercise. And so we've got an equation here. Notice written as some function equaling 0. So that means that this is our f. This is the expression that when I set it equal to 0 gives me my equation. And I would like to take this expression in which x, y, and z are all just input variables, right? And I don't have any evidence at this stage that x, y, or z can definitely be viewed as a function. But that said, how would I compute this partial derivative right there? And I want to start off by noting that this is a presumptuous question. This question is treating x as if it's a function when it's not at all established that it is. Super presumptuous. And sadly, this is how real life tends to come at you, right? People routinely gloss over this huge point about, okay, look, we better make sure that we're not accidentally taking the derivative of a bicycle, right? So when you see a question like this, it is part of your job as the mathematician on the scene responsible for making sure that math goes appropriately and that there's no garbage written down on the page. Part of your job is to recognize that step 1 is to entertain the question first, unprompted. That, we better figure out for sure that x actually is a function of y and z before I actually start pretending that it actually is. All right, so now how do you do this? How do you establish that x actually is a function of y and z? Well, we have our implicit function theorem. And the implicit function theorem says that whatever variable you want to be a function, we take the partial with respect to that variable. Okay, a really easy mistake to make, by the way. A lot of people think, okay, well, eventually I'm going to want the z partial, so I guess I'll take the partial with respect to z. But no, that's not right. It's the one that you want to view as being a function. You take the partial of f, previously agreed that f is that thing. It's that thing whose level set we're looking at, right? That's the function that we need to take the partial of, and x is the variable I need to take the partial with respect to. Everybody cool? Yeah, that partial derivative is actually pretty easy to compute, right? You just straight up just, take that partial, and you get this expression right here. Now, is that equal to 0? Well, very importantly, we're looking at this point. At that point, that partial derivative is 4, which is indeed not 0 as required. And so, happy conclusion, yes, you can treat x as being a function. Is everybody good? Which means that the presumptuous question that got asked of, hey, how do I compute a partial of x? That presumptuously just assumed that x is a function, treating it like it's a function as if they knew that, which they didn't. We've now established that, that's fine. X actually is a function, and so therefore it is reasonable to talk about its z partial. Now, next, how do we compute that z partial? Well, here's our formula for how to compute partial derivatives. Remember the minus sign. Again, this is arguably the most important part of it right there. Make sure to write that down first. Don't say I didn't warn you. Right? So that minus sign is huge. And then my little favorite little memory trick for how to remember what the partial of which partial divided by what partial. Remember that it's the one where if you were to pretend, inappropriately, of course, but if you were to pretend that these kind of canceled, it's the one that when you did that move would actually give you what you want, right? So as a memory tool, this is actually pretty handy. I need z in my denominator, so the numerator's denominator is partial with respect to z, and I need x in my numerator, aka the denominator of the denominator, right? So I think that's a really nice little memory trick. That's how I remember it. I find that very convenient. And and again, don't forget the minus sign. Again, really the most important thing, right? And there's our formula, and now it's all plug and chug. And then you got to compute these partials and plug in the given point, and a little bit of algebra and arithmetic, no big deal. And there's your answer. Everybody good? Yep.
So since this is like locally, does that mean that at other points if the...
Yeah, no, that's right. This is only established at this point right here. And I say near because if you want to view it as a function, you need at least a little bit of wiggle room, nearby. But it's only at this point that I know anything. And because it's only at that point that I've established that this is non-zero. If you look at this expression right here, different color. This expression right here, if I were to pick a different point, it could totally be 0. In which case, crash and burn, and I'm dead in the water. Yeah. Okay. All right. Okay. Moving along, let's see here. I did that. Okay, so moving along, we're going to talk about directional derivatives now. Directional derivatives, honestly, kind of a rehash of stuff we already know. It's largely just a matter of terminology and notation. So don't look for anything too meaningful here? Anyway, here we go. Now let me just remind you, old news, Jacobian matrices do this. Right? Jacobian matrices relate input velocities to output velocities. Right? That was our big interpretation of Jacobian matrices. Fine. And I can multiply by dt. I can think of Jacobian matrices as well as relating input changes to output changes. It's just same statement, in a different sort of form. Okay. Now, let's think about what happens if my function is, as I have it here, only has a single output value. Now, we've talked before about what happens when you have a single input. When you have a single input, you're talking about a parametric curve, and the Jacobian becomes a velocity vector. Here I have a single output. Outputs correspond to rows. And that means that our Jacobian is not a column. Our Jacobian is just a row. And in fact, if you take a closer look at, and again, here we have rules for how to write a Jacobian matrix. These are the elements of the Jacobian matrix. Notice it happens to be that it's just the partials of f with respect to all of its input variables. It's the gradient of f. You're written as a row matrix instead of as a vector, but element for element, it's the exact same thing. Does that make sense to everybody? So that's kind of neato. And that means that I can take these equations up here and I can rewrite them as statements about dot products. Matrix multiplication, when you have a single row, and remember how you multiply a matrix times a vector, you go, dot products of the rows with the column. If there's only the one row, then it's just literally a dot product. So what we have then is kind of an alternative point of view on the chain rule. Now, very useful in some circumstances. But nothing new. It's just a new angle. It's a new take, right? But it's really just a special case of the chain rule. Okay, so the gradient vector is the thing that when you dot it with input change or input velocity, you get output change or output velocity. Dot product with the gradient, aka multiplication by the Jacobian matrix. But in this case, real valued function and all, we're viewing it as dot product with the gradient. Okay. All right. So what is a directional derivative? A directional derivative is just a special case of this. It is a particular special case, and that is the special case where our input velocity is a unit vector. So, unit vector. Well, okay, fine. I mean, it does remain that the chain rule is still, that df dt, how fast the function is changing, or what the output change is relates to the input velocity by way of dot product with the gradient, and that's just a restatement of what we have on the previous page. So all that we're doing here is, so again, we're sort of adding an additional condition that if this is a unit vector, then we're going to consider this output change to be this special thing called a directional derivative. So direction, you can and I think should think of directional derivatives as being just kind of a special case of the chain rule. Is that okay? Yeah.
What's the notation? The D.
Yeah. So this is just notation for this thing called the directional derivative. The notation, you're right. I've got to tell you what is the function whose output values I'm trying to keep track of here. And I have to indicate, in what direction am I moving? And the idea here is that being a unit vector, this u represents a direction. And by the way, thus the term directional, because u indicates a direction. So this notation right here is just how we, it's arbitrary, but it's this or something similar to it. Most books, most contexts use something kind of like this to represent directional derivatives. Yeah?
Is the gradient of a vector in this case, wouldn't the dot product be a scalar? So what does that tell you about direction?
Correct. What this is saying is, and it is important, at least the way we're doing it here, that this f be real valued, right? So it's a single valued function. And so you go back up to this picture, the directional derivative, how fast is the function changing? Well, the value of the function by assumption is real valued. And so if I want to know how fast the value of the function is changing, if that value is a number, then I'm asking for how fast is that number changing. And the rate of change of a number is a number. Right? And so yes, this as it should be is a number. Yeah. Does that make sense? Yeah. Cool. All right. So again, as previously noted, this is a special case of the chain rule. Okay. Now, I think there's another nice point of view on this, and that is, that it's a generalization of the idea of a partial derivative. And let me talk you through this point of view. If you think about what a partial derivative is, a partial derivative says, and again, there's different pictures you can draw, different points of view you can take, but our sort of, our literal picture of the function point of view says that a partial derivative means I'm going to move in the direction of just one of the variables. The other variables all have to stay constant. So I'm moving in the direction of one of the variables, and I take the derivative, namely I want to know how fast is the function changing as a result. Okay, well that's what you do with a directional derivative. A directional derivative says you just have to move with your input velocity being a unit vector. Well, E1 is a unit vector, right? And then you're keeping track of how the function changes. So partial derivative and directional derivative have a lot in common. The only distinction is that for a directional derivative, let's see here. I'll do it like this. For a directional derivative, I can go in any direction. Still, it's got to be a unit vector. Directional derivative means go in any direction. Partial derivative means specifically unit vectors in the direction of axes. So, for example, in the x1 direction or specifically in the x2 direction. So, sure, partial derivatives, directional derivatives very similar. Directional derivatives just kind of generalize it in the sense that, well, you're allowed to point whichever way you want to point. I think that's a nice point of view. Okay. All right. So here is a nice little argument. I think this is an important point of view on directional derivatives. I claim that you can interpret a directional derivative as the rate of change of the function with respect to distance as you move. It's not a derivative with respect to time. It's a derivative with respect to distance. We're going to use lowercase s as a fairly standard label of distance that we've traveled as we move in the domain. So now, why is this true? There's a tricky little argument that gets us to this. And first thing I'm going to do is I'm going to say, well, look, whatever my velocity is, if I'm just moving with some arbitrary velocity, that velocity can be thought of as a direction and a magnitude. This goes all the way back to like first day of class. We represent directions with unit vectors, and we represent magnitudes. If you're thinking of the vector as representing a velocity, the magnitude is the speed. And I'm going to use v, scalar v, to represent speed, where vector v represents velocity. Is that cool? So you can do this with any non-zero vector. The unit vector to represent the direction, magnitude of the original vector represents the speed. Okay, and with that said, real slick little move here. Here's that equation. I'm going to take that equation and I'm going to dot both sides by the gradient, free country, right? And now let's just look at what I've got as a result. What does this tell me? Well, the chain rule tells me that on the left I have df dt. Right? That's our interpretation of the chain rule from 2 pages back. On the right, I have speed, and now I appeal to your physical intuition. Speed is distance per unit time. Yeah, is that cool? Now, let's look at what else I would have to put in this equation down here. What is it that I multiply by ds dt to get df dt? In single variable calculus, chain rule tells me that whatever goes here has to be that. So, well, if these equations are equivalent, and if that's equal to that, and that's equal to that, well, that means that this thing, the directional derivative, has to be this thing that makes the second equation work. I said differently, that means that directional derivatives are rate of change of the function with respect to distance traveled. So a nice little metaphor. If you imagine yourself driving along a mountain road, right? And as you drive along, you're keeping track of your altitude, right? It's kind of a fun thing to do. My ears pop a lot. So I'm very interested to know, have I gained 1,000 feet recently? Because then my ears are going to hurt, right? So as you drive, you can talk about the rate of change of altitude with respect to time. And that is in, feet per second, right? And that depends on how you drive. As you're driving along this road, if you drive faster, you're going to gain more altitude faster because you're moving faster. I think that's pretty satisfying, right? So rate of change of altitude with respect to time depends on how you drive. Rate of change of altitude with respect to distance doesn't. It really only depends on the road, right? So for every 100 feet that you drive, you gain a certain amount of altitude just depending strictly on how steep is that road. Drive faster, it's still the same amount of altitude gain per unit distance traveled. It doesn't depend on the way you drive at all. Right, so I think this is an interesting distinction to draw. This equation relates two different things: rate of change with respect to distance, rate of change with respect to time, and I like to distinguish between the road and the road trip, which I like the way that rolls off the tongue, right? This df dt is about the road trip. It's about your personal experience as you drive along the road. Maybe you drive really fast. I drive hopefully slower. I don't know. But you drive faster, you drive slower, you're going to have a different df dt, right? This is just about the road, only the road. The road does not care how you drive fast, drive slow, whatever. But altitude gain per unit distance is all about the road and only the road. So make sure in your mind to understand the difference between the road and the road trip. And these two things are related to each other, but they're not the same. And specifically, the directional derivative is about the road alone. Okay, good stopping point. I keep going over. I keep thinking that I can get stuff done faster than I can. Sorry about that. We'll draw the line right here. We'll pick up here on tomorrow. See y'all later. Have a good one.